Hi guys, in this tutorial we'll demonstrate how to determine the moment of inertia of the area shaded here. So what we're seeing here is a case where we have the area that we're kind of looking at here is an area that is between two curves. Yeah, that's the region we're going for. Now there are two methods that you can actually use to determine the moment of inertia of that area about the x-axis. In one of the methods, you directly go for that area that is shaded and find the exact area, the exact moment of inertia. But that method might not be appropriate or might be hard to deploy, especially when you're looking at very complicated shapes. Now, for such shapes, you're going to see how the second method is going to be very effective in the sense that you can easily get the moment of inertia about the x-axis for the upper curve as if it was the whole thing like that, and then after that, from that moment of inertia, you then subtract the moment of inertia of the lower curve. So the moment of inertia of a lower curve, notice that it to be the moment of inertia of this section here. So you get the difference between the two solutions, and that is going to give you the moment of inertia of the shaded section. Now, let's demonstrate both methods so that you guys are comfortable regardless of what you have to use. Now for the first part, we just work out this. So again, what we're trying to determine is the moment of inertia I about the x-axis. So about this axis here. So this is what we're trying to determine. So method one. So it's up to you which method you're going to favor here, but I'm showing you both methods because the second method is going to be very helpful for composite structures where maybe it's hard to directly get the moment of inertia. Okay, now if we're going to get the moment of inertia directly here, then the most appropriate choice here is going to be to choose a horizontal section. So if you want to get the moment of inertia about the vertical axis, that is about the y-axis, then in that case, the most appropriate choice might be to select a vertical cross-sectional area in something like this. That is if you want to get the moment of inertia about the y-axis. This, of course, as you saw in the previous video, will ensure that the distance between the axis and the selected section will be uniform for all the points on that section. But since in this example, we are going for the moment of inertia about the x-axis, we go for a horizontal cross-sectional area, again, so that it ensures that the distance from the section to the x-axis will be uniform. So let's reduce this in size a bit. Okay, so again, we select our section strategically so that we can utilize the points here and the points here, so that at those 2 points, we'll take advantage of the relationships governed by those 2 equations. Okay, once that has been done, let's put down our equation for moment of inertia. So the moment of inertia about the x-axis, Ix, it's going to be equal to the integral of the distance from the axis, which is the x-axis in this case, to a differential section. In this case, when you look at the distance we're going for, it is basically just going to be a distance from here coming all the way up to there. And this distance, notice that it will be literally the same as the y value there. And of course here, what we have is, I'll label this as x. I'll label this as, I'm saying this is 1 and this is 2, so I'll label this as x2, so that it will relate to that equation. And I'll label this point here to be x1, so that it will relate to this equation. But of course, you can use any labels, really should still be okay. So if you look, of course, this y here has nothing to do with that equation. So perhaps I should put it somewhere here. So what I was saying is the distance between the axis we're going for, the x-axis, and the selected section is basically just going to be y. So in this case, what we have here is y squared. But then this has to multiply with dA. Now what will be our dA? The selected section is something like this. And in this case, when you look at this part, I've labeled this point to be x2 and this point to be x1. So the distance between them will be x1 minus x2. So here what I have is x1 minus x2. And the thickness here, if you look at the thickness, it is in terms of y. So because of that, this thickness will be taken as dy. So this is what we have there. We have our dy. Therefore, our cross-sectional area dA will be equal to that width. So we have x1 minus x2 here, and then multiplying dy there. So when we plug in our dA, we now get our expression for moment of inertia as the integral y squared there. And then we have x1 minus x2, and then we have dA here. But this x1 and x2, what are they? How can we express them? Well, let's come back to these equations. What you see here is that x1 is governed by this equation. So I can say this is y. Notice that for these two lines, the values of y are the same. What I'm trying to say there is, because in this case, the two lines have the same value, meaning the two graphs, this equation and this equation, the values of y will be the same. So we'll just take the value of y to be y. So for the bottom boundary there, y is equal to 1 over k1, and then we have x squared there. But this x here is the one that is going to point towards x1, so I can even assign it x1. From here, what you see is we end up with ky, y is equals to x1 squared. So that if we wanted to find what x1 is, we just have to get the square root of k1 and y. So this is what we'd have to do. On the other hand, to find x2, x2 will be related to that equation. But again, at this point at x2, the value of y, which is y2, will just be equals to y. So you have y is equals to 1 over k2. And then we have x2 raised to the power 1 over 2. From here, we get k2 y equals to x to the power 1 over 2. So that in the end, if we wanted to get what x is, square both sides, x will now be equal to k2 squared and then y squared. So these are the two values for, the two expressions for x1 and x2. This was x1, this is x2. Let's just put subscript 2 there. We can now get these expressions for x1 and x2, substitute them where we need them. So we have that's root k1 and y, where there's x1. So we have this. And then minus where we have x2. Where I have x2, we have this expression. So that is what we have there. And then this is multiplying. Oh, this is not dA. If you remember, we already factored in this is dy, not dA. So I hope you guys saw that. So this is not dA. It is in fact dy. It was dA when it was this, but we've plugged in what dA was. This is how we ended up in this this position. Hope you guys were able to see that. Okay, so this is dy here. So you still have that y squared here. Then we have this. Then this is ix. Now at this point, you can also try to work out what the values for k, what they are, or you can do it later. Let's do it now. See, from our description of the equations here, we quickly notice one thing. You see, at each point here, at this point, the values of each equation, they're going to be, as in the value of x there is going to be, we're going to have x there is going to be equals to a, because we are seeing that this equation goes all the way, as in this line, goes all the way up to there. So at this point, x will practically be a, but b will be what? As in y will be b. So what happens? See, at that point, when x is equals to a and b is equals, not b, sorry, and when y is equals to b, what happens? Let's pick the first equation that gives us 2, y2 I mean. From the equation of y2, what we see is that, you see, k1 and k2 are constants. So if we have a point where we actually know what what x and what y is, it implies that we can actually determine what this constant is. So here, of course, when we plug in a to be b and a to be x to be a and y to be b, we end up with b is equals to 1 over k2, and then where there's x, we'll put a raised to power half. What this is telling us is that k2 is actually just equals to a to the power half over b. This is the expression for k2. In a similar way, we can get the expression for that's y1. We can get the expression for k1 from that expression. You see, both equations at this point will have the same value of a and the same value of b. So you can just copy that. So they'll have the same value of same value for x and the same value for y, and that is a and b respectively. So again, for this equation, when y is equals to b and x is equals to a, we end up with this k1, and then this is a squared. So here we see that k1 will be equals to a squared over b. We can now get these expressions and substitute in our expression for ix. Let's see what we end up with there. So getting this, now where there is k, we'll plug in that and simplify. So let's stretch this a little, and we see here we have root kx. So instead of root k, that not kx, ky, that becomes root, where we have k, we have a to the power half over b, and then this is just k, remember, but we also had that y there. And then here we have k again, but now we don't have a root. So here, where this k is squared, I hope I haven't substituted wrongly. This is k1, which is here. This is k1. K1, I'm putting this one here. Sorry for that. So what is k1? We're putting this one here. So I plugged in the one for k2. So where is k1? Let's do this again. So what we do is this. So this is root k1y. This becomes root, where we have k1, we have a squared over b. And then we still have that y there. So this is now k1y. And then apart from that, now we plug in for k2. So where we have k2, we'll now put that. But remember, k2 is being squared. So this becomes, where there's k2, we'll have a 1 over 2 over b. But again, k2 is being squared, so we'll square that. We now just have to simplify this, and seeing that a and b are constants, so I'll just separate the square roots there. So that I have y squared, and I separate the square. This is going to be a over b to the power 1 over 2, which is just the square root of b. And then the other side, I'll have the square root of y, which is 1 over 2. I'm doing this so that I can easily identify this, that it won't be affected by the square root, by the integral I mean, and drag it out. Now I'll only have these two from this term, and since they are multiplying, I'll just add the powers here. So this is from the first term here, so these will just add the powers. So when you add 2 plus 1 over 2, this ends up giving us 5 over 2 as the power. So that we can just look at this as y to the power 5 over 2. And then this is, of course, dy. So I've just multiplied this with this term. Now what I have to do is do the same thing to the second term, but the difference here is we have that minus. So these two are already separated, so I'll just bring in the square there. A to the power half, and then raised to power 2 again, that just becomes a. And then this, of course, will still be b squared. Now we have the integral here. The y to the power 2 and y to the power 2 here will give us y to the power 4. So now I have y to the power 4 dy. So this is now what we're looking at. Now because we're integrating with respect to y, so the limits will have to be in with respect to y. So the values of y are changing from when they are lowest here, when y is equals to 0, and max when y is equals to b there. So our limits of integration are when y is 0 to when y is b, y is 0 to when y is b there. So from here, we can simplify this expression by integrating. We now have a b to the power half. When we integrate, this becomes y. Add 1 to the power, that becomes 7 over 2. So we have power 7 over 2, then divided by 7 over 2. So this is what we get, but this is from 0 to b. Minus, this is to a over b squared. And here as well, we have, this becomes y to the power 5 over 5, also from 0 to 5. So this is what we have. Now all we have to do is plug in the limits. When y is 0, the whole thing just gives us 0. So go for when y is b. So this is now a. Sorry, this coefficient is only for this part, and this coefficient is for this part. So don't get them confused. These are in pairs like that. So this is a over b to the power half. Then when y is b, we get b to the power 7 over 2 over 7 over 2. Of course, changing this from division to single fraction, you should see that the 2 will go up. We now have 2 b to the power 7 over 2 divided by 7 b to the power half here. So this is just the first term. We still have the minus here. This part, when y is 5, we get a y to the power 5 over 5. Now this is when when y is equals to b, this becomes b to the power 5. And this is 5b squared. We know the powers here will subtract, so that here, this is actually now this just becomes a b to the power 3 over 5. So we still have that a b to the power 3 over 5. But here as well, we see that this is b to the power 7, b to the 7 over 2, that is, and then this is b to the power half. Powers are the same, so we'll subtract. So this, of course, will just reduce to 2a. This will then just become b to the power 3. Of course, this is going to be 7 over 2 minus 1 over 2, which is going to give us 6 over 2, which is just this 3 here. Okay, so having followed that, this is over 7 still, then minus a b to the power 3 over 5. These are like terms, so they can interact. So this becomes the common denominator. We'll take the common denominator as 35. And then we'll just cross multiply the terms here, as in 5 will multiply the 2ab to the 3. This gives us 10ab to the 3 minus, then this is 7ab to the 3. From here, we see that this reduces to just 3ab cubed over 35. So of course, the units, we know the units for moment of inertia. So whatever the units are, to the power 4. Now, this is the moment of inertia Ix determined using this method. Now, you have to remember, this question was specific. They actually said A is 6 centimeters. A is 6 centimeters. And they're also saying that B is 4 centimeters. What are we doing then? You can then get these values, given that this is that and this is that, by clearly showing all your working. Okay, so we have this. You can get these values for A and B, bring them to this expression, and substitute them. So if we did that, notice that our Ix will now be found by just saying 3, where there's A will put 6 centimeters, where there's B will put 4 centimeters, but the B has to be raised to the power 3, and then this is divided by 35. Notice that when you evaluate this, the units will come out correctly as centimeters to the power 4. But you guys can do this on a calculator and see what this will give you. The key thing is you must have been able to arrive at this position. Okay, now let's show you another method that you could have used, which is going to be a method that is going to be very handy when you're dealing with composite structures or composite areas. Now, let's look at the same question, but now we want to look to use a second method. So let's say this is method 2. Now, how will this work? Well, like I pointed out earlier, for this method, what will take advantage is one property of moment of inertia. See, if you have the moment of inertia of a sphere or a circle like this, the area of a circle like this, let's say you have this shaded region here. So if you have the moment of inertia of the shaded region as, let's take this moment of inertia to be I1, and you have a circle inside and you know its moment of inertia, let's take this as I2. It turns out that if you now wanted to find the moment of inertia, not of the whole circle here, but instead the moment of inertia of that, but just of a section between the outer circle and the inner circle. So of course, let's say this is centered at the origin, and when you're determining the moment of inertia, perhaps you were getting it about an axis, let's say the x-axis somewhere here, and even here, you know the moment of inertia about the same axis here. And even for this one, it was the moment of inertia about that same x-axis. So what this implies is that if you now wanted to find the moment of inertia of this region just between the two circles, if you wanted to just find the moment of inertia for this section, how would you do it? Well, it turns out you can just get the difference in their moment of inertia. So since the moment of inertia was evaluated about the same axis and nothing really has changed, it turns out that the moment of inertia about the x will be equal to the moment of inertia of the whole circle as if there was nothing inside, as if it was just complete, minus the moment of inertia of the hole that is being poked inside, which is the moment of inertia of that circle inside. So this is the property that we're trying to take advantage. Now, how do we use it? Well, in this case, what we have are not two circles, but instead we have two curves. So let's see. What we'll start by doing is we'll get the moment of inertia of the upper boundary, the upper curve. So we'll get the moment of inertia of this area here. So this will be everything. So how do we get the moment of inertia of that structure or that pass? That part. So choose a differential section like we saw in another example that we did. So choose a horizontal section like this. We're not choosing a vertical section will lead us into the parallel axis theorem. So we'll choose a section like this. Okay, so that is the section that we're going to select. Now, how will it work? Well, in this case, just like we saw, the section will not end here because we're going all the way up to the end. So for this section, we know to say it stretches all the way up to there. Let's make this smaller. Okay, so the section in this case goes all the way up to the end because we are disregarding that lower boundary and just getting everything below that y2 graph. So how will it work? Well, it's similar to what we did, so I'll be a little bit fast there. I'll label this as moment of inertia 1. And for this one, we'll say it's the integral of the distance between them. The distance will be y, so we'll just square it. Y, of course, being up to there. We're taking advantage of this being y here and this being x here. So we have this dA. For the section selected, you have to see, like we did again in the example that we did some time back, has to be a minus x. This is dy. So that what we have is the integral from 0 to, we're integrating with respect to y, so this will be to b, and then y squared. Then this is going to be a minus x, and then dy. So how do we proceed from here? What is x? Here the connection is that equation, the upper boundary, which is y is equals to k that is 1 over k2, and then we have x to the power half. So just like we saw in the previous method, we know what x and y, what they are there, so we can still use them to figure out what k2 is here. So when y is b and k and x is a, we have that expression. What will be k2? So in this method, let's see what we get. We still get the same expression for k2. This would imply that k2 would be equals to a to the power half over b. So we get two things here. In the expression that we have, in the equation that we're given there, we can make x the subject of the formula because x is what we want to substitute here. But we now know what k2 is. So what we get, we make x the subject of the formula there. We have k2y is equals to x to the power half. So that when you put where there's k2, we put a to the power half over b, then y is equals to x to the power half. We square both sides. We now get x is equals to, when you square both sides, this will just be a, this will be y squared, and this will be b squared. That is if we square both sides. So this is what we'll bring and substitute where we have x here. Doing that, let's see what we get. We get this. But where there's x, we plug in that expression, which is a y squared over b squared. We now integrate this. So this is going to be first from 0 to b. Bring down a, y squared dy minus a and b are constants now, a b squared. Then now we're integrating the y squared gives us y to the power 4 dy from 0 to b again. At this stage, we just have to integrate this. So we have a, then this is going to be y to the power 3 over 3, 0 to b minus a over b squared. And then we have y to the power 5 over 5 from 0 to b as well. So plug in those limits. We get a b to the power 3 over 3 minus the other side, we get a b to the power 5 over 5b squared. Here, this and this will simplify so that we now have a b to the power 3 over 3 minus, this is going to be the a b to the power 3 over 5. And let's see what this gives us. 5ab to the power 3, 3ab to the power 3 over 15. And finally, this comes to give us 2ab to the power 3 over 15. This comes to be our expression for I1. Now, having obtained the expression for I1, we now want to get the expression for I2. So I2 will now give us the moment of inertia of the area below that second graph. What is that? So we now want to get the moment of inertia of the area below this function. So this is now the moment of inertia of this part. That equation, of course, being y is equals to 1 over k1. Then this is x squared. Is that x squared? Yes, it is. Okay, so for this part as well, what we will need what k1 is. So let's see what k1 is. So when x is a and y is b, we have b is equals to 1 over k1, and then this is a squared. So that we see that k1 will be equal to a squared over b. So why do we need that? It's something that we did in the previous step. We determined also what x was, so we just write x as the subject of the formula for this expression, and x will be equal to the square root of k1 y. But we know the expression for k1, we'll plug that. We get the square root of a squared over b and then y. So we'll need those later. The first thing we did was to highlight a differential section. Again, about the x-axis, the most appropriate section will be a horizontal section. So we go for the horizontal. Having selected it, we want to utilize, of course, make sure this is literally at the edges there so that we use that boundary. We'll take this to be x here and this to be y here. So just like we did in the previous step, the moment of inertia I2, we'll label that as I2, which is below that second graph. So that is going to be the distance. Again, this is y squared and then the a. So just like before, we'll still have something like this. The difference is now when we say a minus x, our x will now be controlled by this expression here. So this will be what our x will be. So we'll just copy this and put it where we have x. So we'll say, of course, this is still dy. We'll bring that x when we have to substitute it. This is the integral of y squared, and then this is a minus x. Then we have dy. The limits, it's still with respect to y, so this is still from 0 to b. So now this is 0 to b, y squared, and then a minus, where we have a, our expression for a in this case, which is this. And then we have dy. So we now just have to simplify this, distribute the integral. So we get a here from 0 to b, then y squared dy, then minus. So I'll split this root so that the constants can come out of the integral sign. The root of a squared will just be a. The root of b squared will remain the root of b squared. So just write it as 1 over 2. And then this will remain as the root of y. So this will be the integral of the y squared, which is this one, will be multiplying the root of y, which is 1 over 2, then dy. This is still from 0 to b. So the first one can be evaluated. That is going to be a. Then y to the power 3 over 3. This is from 0 to b. Minus, this is a. B to the power 1 over 2. And then this is now going to be the integral, same base, add the powers. That is going to be 5. That is going to be y to the power 5 over 2. And then dy. Let's see what we get here. This is a, y to the power 3. Of course, plug in the limits. This becomes b to the power 3 over 3 minus. The second part here will become, when we integrate, of course, let's see. This is still a over b, 1 over 2. But the integral there, the limits are still from 0 to b, of course. When we integrate, we'll get y to the power 7 over 2. And then this is divided by 7 over 2. This is from 0 to b. So simplify that a little bit. Minus, the 7 over 2 is a constant. The 2 comes up. We now get 2a. Then this is over 7b to the power half. When y is b, we just get b to the power 7 over 2. When y is 0, of course, everything dies. So here, same base, we are dividing, subtract the powers. We see that we will have a to the power, b to the power 3 over 3 minus, this will be 2a b to the power 3 over 7. We now combine these two expressions into a single fraction. They are like terms. We get 21 here. This will be 7 a b to the power 3 minus, this will be 6 a b to the power 3. So that in the end, we have a b to the power 3 over 21 as the second moment of inertia. Now, using that concept where we say if we have the moment of inertia below this, and now we have just determined the moment of inertia below this function, which is this one. So we can just get the difference between the two, and what we end up with will be the moment of inertia between those two graphs. So this is what is going to give us this. And the moment of inertia between the two graphs, we'll label that as now I. Notice that I1 and I2 were both evaluated about the x-axis. So even the difference between them will be the moment about the x-axis. So in other words, the moment of inertia about the x-axis will now be seen as our I1 less our I2, because our I1 contained the entire area there. So what was our I1? So when you go back up, our I1 was this. And our I2, we just seen what our I2 was, we found this. So let's get the difference here. So common denominator, this will be 15 by 21, and then this will be 2 by 21, which is 42, AB to the 3, then minus 15, AB to the 3. From here, the difference on top will be 27, AB to the 3, over the product in the denominator will give us 315. Now from here, we just simplify this, divide both the top and the bottom by 9. And what we're going to get is going to be 3ab to the 3 divided by 9 into 315 will go 35 times. Notice that this expression we have obtained is the same expression we obtained when we used that other method where we just went directly. Because from here, we can get the moment of inertia Ix. Again, not I1, Ix. You can get what Ix is by just plugging in what A is and what B is. Of course, those values were given in the question. So that is A is equals to 6 centimeters, B is equals to 4 centimeters. So we have, where is that? We have 6 centimeters and 4 centimeters. Plug them in here and you get your answer, and it will be in centimeters to the power 4. Okay, all right guys, hope you found this helpful. Leave a like if you did, and we'll see if I'll be able to upload more on the concept. All right, see you in the next class.